but it's not my fault. So I'm going to present an introduction to myself, and then tell you sort of the story of my life from the point of view of a young person. So the part that I think you can learn from, and then draw some lessons from it. So about my formative years. This was a while ago, and you can see my family was not very wealthy. I grew up in Queens, New York, but my family was very dedicated to education and to my success. And you can see that when Christmas came, there were lots of toys and presents that I stayed up very late playing with. And my parents, as I said, we didn't have a lot of money, but they did always supply me with toys and books. When I was growing up, was in the time of the Cold War, and I vividly remember the atmosphere of fear and competition that was very prevalent in the United States in the late 1950s and early 1960s, my childhood. The positive side of that, from my point of view, was that at that time in the United States, the power of science was very evident to the country. People felt that the future of the country, the security of the country, depended upon having people who were very capable in science. And great stress was put on education. Scientists were heroes. They were the people who were going to protect us. And they also had magical powers. They could make things blow up. They could put satellites into space. And when the Russians put the first satellite into space, this was a wake-up call for the United States that people were quite shocked by. I grew up having heroes, role models. This is, maybe you heard of him, Albert Einstein. This is Bertrand Russell, who's another great hero of mine. And I made it my practice when I was growing up to try to read everything of theirs that I could find. And that was a very good preparation for my later life. I didn't realize it at the time, of course, it really was crucial. My parents, as I said, made great sacrifices for my benefit, and I got more sophisticated toys as I grew a little bit older. And my father would take me to a bookstore, which was not very far away. And I could buy any book I wanted if I used my own money. But if I bought science books, he would pay them. So I didn't have very much money, so I got a lot of science books. And this was when I was Beginning, yes, I used to be quite different. This was when I was beginning university. I went to the University of Chicago. It was really the first time I spent away from home for very long. And it was a very exciting time. And then I went to, I finished my undergraduate education, and I was very young. I had done everything very quickly. I went to graduate school at Princeton at the age of 18. And I didn't know what I wanted to do. I knew I wanted to do something with mathematics. I really liked mathematics. I originally thought that I would try to apply mathematics to understanding how minds work, but minds turned out to be too complicated. And really, I went to Princeton as a student of mathematics, but didn't really know what I wanted to do, and kind of was lost for a couple of years. But then I wandered around. I explored what was going on in biology, what was going on in chemistry, as well as in mathematics. It happened that at Princeton at that time, the mathematics and physics departments shared a building, so it was very easy to wander over to the physics department and hear what was going on. And this was now the early 1970s. It was a very exciting time in physics. I sensed that, and I met a very charismatic, at that time, young professor. Well, I thought he was very old, actually, because he was about 10 years older than me. He was maybe 30 or so at that time. But he was very charismatic, very ambitious, very energetic. This was David Gross, and I decided, with this excitement in physics going on and this young person I could work with, to jump into physics, and that's what I did. And that led directly the work we did rather directly led to the Nobel Prize a bit later. So let me tell you a bit about what the work is. So we know 4 fundamental forces in our description of nature. There's gravity. There's electromagnetism. Gravity, of course, is a very familiar force. Things fall down. There's been a wonderful theory in physics of how gravity works since the 17th century. Isaac Newton, his famous law of gravity, kind of a model of physical law. And it predicts all kinds of things about how planets move, how tides work, and so forth. It is the foundation to this day of most of astronomy, and now there's an even more beautiful theory of gravity, the general theory of relativity, which dates from the early 20th century. Electromagnetism is, again, kind of a familiar force by now. We know about electricity, we know about magnetism, we know about electromagnetic waves, they operate our cell phones, and so forth. Has been in physics a beautiful theory of electromagnetic forces, unifying electricity and magnetism, predicting many, many things. Actually, turns out to be the foundation of chemistry as well. But the fundamental equations have been known since the 1860s, Maxwell's equations. But in the 20th century, when physicists started to study atomic nuclei, subatomic phenomena, they discovered that those forces were inadequate. those familiar forces. There are two more forces that one needs in order to account fully for the phenomena of nuclear physics and forces of nature. These are called the weak force and the strong force. The weak force is responsible for transforming elements. So the power of the sun derives from changing protons into neutrons. This is something that's possible with the weak force and liberates energy in the fusion of, what's up? But that leaves the force that holds the atomic nuclei themselves together, the most powerful force of nature, is something else. It's called the strong force. Originally, the problem was that in the theory of atoms, we discovered that atoms consist of a large cloud of electrons, well, relatively large, of course, atoms are very small, but a relatively large cloud of electrons, that inside almost all the mass and all of the positive charge is in the atomic nucleus. The electric forces want to blow the nucleus apart. Gravity is very, very weak, so what holds them together? So people just named the force the strong force, but they had no idea what it was. And so these phenomena that go beyond gravity and electromagnetism were discovered in the early 20th century, but there were no beautiful equations for them, and they were hard to study because nuclei are very, very small. So it was top of the physics agenda to figure out what the strong force was. Could we find a nice equation for it? So people looked inside protons to see what they're made out of and what the basic forces are that operate in that realm. I should say that the forces between protons themselves are very, very complicated and do not have a simple mathematical description. But people hope that by looking inside protons, you find simpler things that satisfy simpler equations where you could have a nice theory. And the key discoveries were made using a very fancy microscope called the Stanford Linear Accelerator. It doesn't look very much like the kind of microscope you'll find in your freshman physics laboratories or chemistry laboratories. It's a long, long line, linear, 2 miles long, where electrons are accelerated to very high energy, and then at the end, bang into protons. And when you analyze what happens in those collisions, you can, by using some very sophisticated image processing, figure out what's going on inside protons. The pictures, snapshots of the interior of protons. I'll just mention, because it's amusing, that this linear accelerator crosses the San Andreas Fault, where the Earth is moving when there are earthquakes. I don't know why you built an accelerator like this across the fault, but people, you notice that on the two sides things look very different. That's because they are very different and they move relative to each other. But fortunately, that has not been a problem. There haven't been any large earthquakes during the time that this is operating. Anyway, in studying what goes on inside protons, people found that there are simpler objects inside protons. They're called quarks. And quarks turned out to have a very, very surprising property. That is, although they're subject to the strongest force in nature, this strong force, which is what binds them into protons, when the quarks get close together, the force between them gets very weak. This is very unlike electromagnetism or gravity, where the force gets stronger as things come together.
this is a very peculiar kind of force that gets weaker when the particles come closer together. And that's very difficult to write consistent equations for. That is, things that are consistent with the principles of quantum mechanics and relativity. And so the problem we looked into was, could you make a theory that's consistent with relativity and quantum mechanics, that has a force that behaves that way? And we found it was very difficult, but not quite impossible. In fact, you could do it basically in only one way, and that was a gift from heaven. Because if you can do it only one way, that is the way it's done. And so this led us to a theory called quantum chromodynamics, or QCD. It's a kind of generalization or modification of electrodynamics. I call it electrodynamics on steroids. Instead of having one kind of charge, electric charge, you have three kinds of charge that are called colors. They're not, of course, color of anything, they're just charged like things. And instead of one photon, which reacts to the charge, you have 8 kinds of colored gluons that are photon-like particles that also change one color into another. So they respond to the color charge and also change one into another. And the King of Sweden liked this theory very much. And congratulated us on having achieved it. And it is, to this day, a theory that's now widely accepted of how the strong force works. It has many applications. So now, let me talk about some lessons I drew from my experience in getting from being a student, a child, to a scientist. First lesson is start early. It really is important, especially if you're going to do mathematical work, theoretical work that involves mathematics, that you start early so that it becomes like a second, a native language to you. You don't have to think about the algebra. You don't have to think about the calculus. You just do it as easily as you speak your language. And that brings up another issue. You have to speak English very well. That may change decades from now, but at present, I think for the foreseeable future, the language of the international language of science is physics. There's an enormous literature. Conferences are in English, and you have to live it. Another thing is, I mentioned my years of struggle, my 2 years of struggle. I could have also mentioned that the calculations which led to asymptotic freedom were very complicated calculations. In fact, we didn't know how to do them. I certainly didn't know how to do them when we started. And we made many mistakes, but corrected them. We didn't wait until we understood everything before we did anything. It's very important. Don't be afraid. If you don't make mistakes, you're not working on hard enough problems. So actually, and that's a big mistake. So in your studies, if you're not making mistakes, if you're getting 100% on all your exams, that means you should be studying harder things. And I think this is a problem for many students, especially people who really are accustomed to being perfect. Fortunately, I was not perfect, and you have to be comfortable with the idea that you're going to make mistakes and you keep going, because the work will teach you how to do it. When you're trying to do something difficult, you won't know how to do it at first. In research, if it was obvious how to do something, it would be done, and it's important, it would be done. When you're going into something essentially new, no one knows how to do it. You won't know how to do it. You have to try. Some things will work, some things will not work. And the work itself is a learning process. This, I learned, this is something that I found in a fortune cookie, but I had been living it before. I found it in the fortune cookie, and I think I can share with you now that message from the wisest fortune cookie I've ever encountered. The work will teach you how to do it. Also, as students, you should be active. You should not just try to absorb knowledge. You should explore widely all kinds of things. I've talked about my lost years after graduating as an undergraduate, kind of floundering around for a couple of years at Princeton when I didn't know what I wanted to do. But that was, in a way, a necessary process. I explored very widely. I looked at computer science, it's now computer science, neurobiology, that was my original interest. I had to satisfy the authorities, I had to pretend I was interested in pure mathematics. I went to physics seminars too, and I didn't understand at all what was going on in these seminars, but I sensed the excitement, and that process of exploration turned out to be very fortunate. So go out, explore widely, find out what you think is exciting, find out what you enjoy doing, and then that will be the way towards doing important original work. And as you engage with your studies, it's very important to not just take what's on the page and try to memorize it, but to relate it to everything else you know, to relate it to other things you want to do, to use your imagination in a word. So, you need imagination. However, I also said earlier, you need to learn things, you need to establish firm foundations, you need to learn the language, and both these things are important. But really, the knowledge has to be active knowledge. You have to, as you're learning things, imagine what you can use it for, what you'd like to use it for. I summarize, I was asked once in something called SciFu, is a meeting where people introduce themselves and have to say what their philosophy of life is in 3 words. And most people cheat. They don't actually they don't actually use 3 words. And I think that's really lame. You should try to use exactly 3 words. That's a creative challenge. And I was very proud because I managed in 3 words to say something infinite. My philosophy of life, my method, is to apply this algorithm. Think, play, repeat. And I think that's a very, very powerful recipe. That's also easy to remember. and summarizes a lot of it, really summarizes the essence of the advice I've given you, which is think about what you're learning, learn it, absorb its essence, but at the same time play with it, use your imagination. Think about how it might be different, what's wrong with it, is it not perfect, how can it be better? And then repeat, go back, learn more, play with it, repeat, and soon you'll be, if you redo this and keep expanding, you'll soon reach the frontiers of knowledge and be doing new things. Okay, so finally, let me discuss in a very, very general way some of the things that you, as young people, can look forward to doing in the future. It's not the case at all that science is finished. Far from it. It's not the case that everything has been done. And that's very important to know. You read things in textbooks, they're not complete. There are chapters yet to be written, and you can write them. So one thing you can do is solve mysteries. There are great mysteries out there. One of the mysteries is called the dark matter mystery in astronomy. This is a fake picture of dark matter. The thing about dark matter is it's dark. In fact, it's not dark in the sense of being black. If it was black, you could see it, and you know there was a cloud up there, so it wouldn't be so mysterious if you study the sky. The thing about dark matter is it's totally invisible. The only way that its existence has been detected is because it exerts gravity on other bodies that move. So you can see how the bodies are moving, figure out what gravity is causing those motions, and from that, figure out what the mass has to be that's producing that gravity. And what you find is, in many cases, in fact, basically in all cases in astronomy, when you study how objects are moving in galaxies, how stars are moving around in galaxies, that the amount of matter that you can see, the amount of matter of stars in gas clouds, things like that, the things that you can see in any way using all the resources of astronomy, using telescopes, radio telescopes, cosmic ray receptors, everything. You find that if you add up the matter that you can see in all those ways, it's not enough to account for the gravity that is necessary to account for the motions. And so we introduce, since we think the laws of gravity are very sacred, they're very successful, maybe they're not quite right, that would be very interesting, but at present, what seems to be a more fruitful hypothesis is that there's a new form of matter that escapes current methods of detection. That's called dark matter. And you know where it is because we can see what the missing gravity is like, what the gravity is like, the missing mass that accounts for it has to be. And this is a dramatic example called Bullet Cluster, where you have two galaxies that have collided, and you can map out the amount of mass that is in the kind of the sort that we can detect, counting up stars and gas clouds and so forth. And you find that those two galaxies have collided, gone through each other. That kind of matter has kind of stuck together. It can lose energy and slow down, but there's more mass, and what's plotted here as this purple cloud is the extra mass. So it's not an actual purple cloud, it's the extra mass, and this shows very tangibly that there is such a thing as the dark matter, and where it is in this particular case, and that it's different from ordinary matter, because the ordinary matter is more sticky. So, although it's a fake picture, and in fact, basically all pictures in astronomy are fake pictures, it's sending a very important message. And the challenge is, what is this stuff? People are exploring different ways to see new kinds of telescopes that might tell us, might be able to be sensitive to this new kind of matter. People have theories about what it might be, so another way you can try to make progress in identifying it is to figure out how could our laws be more perfect, more beautiful, what's missing in our equations, and then see if any of the things that suggests could account for what the dark matter is. And I have a pretty good guess for that. That's really an axion, but that's another story. Who can guess what this is? So, I'll give you a hint. It's not noodles. If you look carefully at this, it might give you a clue. Yeah, these are. This is your brain. Well, this is somebody's brain. Or actually, it's more likely to be a mouse's brain. But in any case, brain. And we believe, I said we, many people believe, I think most working scientists believe that this material that produces minds, that produces thoughts, is the same kind of material we study in chemistry labs and physics labs and nothing else, that somehow ordinary matter manages to produce thoughts, produce memories, produce all the phenomena we think of as mind. How does that happen? This is a great mystery. No one knows how memories are stored, really. No one knows how laws of quantum mechanics ultimately can support things like consciousness and sensing things. We know a lot, but what we don't know is clearly much more. There are very exciting opportunities here. In recent years, if I was starting all over again, I very much probably would go into this. In recent years now, because it has become a subject where mathematics is used, there's much more data, tools, big computers, and sensitive instruments that take good pictures of brains are much better now, and this problem seems to be right. There's very impressive applications of so-called neural nets you may have heard of that support deep learning, that have enabled computers to recognize cats, for instance. And so we're starting to understand how networks that have a lot in common with simplified models of nerve cells neurons can function to give thought processes. So now we know how to make computers that beat the best humans at chess, even at Go, and even to recognize cats. But the great world of understanding how mind works is still open. I hope some of you will move that subject forward. You can see new things. Who can guess what this is? It's all right to make mistakes, okay? I want somebody to make a mistake. Tell me what this is. You mentioned it. No, it's not dark matter. Well, what? What this is empty space. This is empty space if you look very, very close. So it's vastly magnified, and if you stretched out time by a lot. So this is what you would see if your eyes were capable of resolving much, much smaller distances, so inside a proton, and much, much faster things than our eyes can resolve. Our eyes were not designed or evolved to look inside protons. But with our theory, with quantum chromodynamics and computers, we can calculate how energy is fluctuating. This is quantum mechanics. Things fluctuate and energy fluctuates. So what you're seeing here is gluons coming to be and passing away. This is happening everywhere, always, and is the fundamental structure of the world. Empty space is not empty at all, and the properties that these fluctuations lead to are exactly the kind of thing I'd have the Nobel Prize for. So this has to be right. Same computations that give this picture have many checkable consequences. Correct. So, like in astronomy, this is also a completely fake picture. Our eyes don't see these things, but we use them to bring the concepts to life. And that art, it really is an art of bringing concepts to life, is an extremely important frontier of understanding. Humans are visual animals. We have very, very powerful mechanisms of interpreting images, and so if you can turn concepts into images, they're much easier to deal with. And that leads to a lot of insight. Who can guess what this one is? This one's not a brain. At least not a human brain. What? Network. It's a network. It's the internet. It's showing connections in the internet and how different nodes are connected to other nodes. You see this is some very popular site. This is, I think, Taylor Swift on Facebook. I don't know what these are. But what is the structure of these things? Can you characterize mathematically this network? If you want to make the communication smooth and reliable, how should you assign extra nodes to distribute the work? These are fascinating problems that are arising now from technology that will challenge the ingenuity of young people and will be very, very fruitful and important. Or if you wanted to censor things, where would you put in the walls? Don't work on that one, please. Some of our human vision, color vision, is based on the fact that we have 3 different kinds of proteins that respond to light differently. So they have different probabilities of being excited by different frequencies of light. If you're colorblind, you have only 2 of these, or maybe one of you is mutated to be very similar to the other one. But in any case, our sensation of color does very poor justice to the amount of information that's in the electromagnetic signals that arrive in our eyes. Can we do better? Can we have technology that gives us more information? That's a great challenge. How do we bring more of the world using our gadgets, using what we learned about physics and technology, bringing more of the world into experience? And as inspiration, we have something called the mantis shrimp, which has not 3, not 4. Many birds and insects have 4. Pigeons have 5 receptors, but the mantis shrimp has, there are different kinds of mantis shrimps. Some of you may have eaten mantis shrimps. I shouldn't do. They are remarkable creatures, and they have, depending on the variety, between 12 and 16 different color receptors, including things that go to the ultraviolet and into the infrared. What are they doing with this information? They have very tiny brains. There are fascinating problems about that, as well as the inspirations. Okay, they find some use for this. Imagine what we could do with that information, and how do we bring it to ourselves? You can make new things. This is an illustration meant to illustrate an artificial neural network. So you have sensors on top, and then you have design connections, and then connections to connections, and make a network. And this turns out to be a very powerful method of computation. As I said, neural networks have been trained to identify things. And so you can teach them. The process of learning in neural nets is fascinating. And the subject to more creativity. I think we're in early days of understanding how this architecture, which is close to the architecture of our own brains, and very different from the architecture of conventional computers, how this works and how it can be improved. Finally, and this is the very last thing, this is kind of symbolic, but this is a fractal, of course. You've probably seen images like this. And there are two things that I want to convey from this picture. One is kind of scientific. That is, although this picture looks, and in some ways is, extremely complicated, you can, or a computer can, you can program a computer to make this picture using a very, very short program. So it's very, to me, extremely profound that you can make a very, very short program that evolves. The computer does many, many iterations and operations following that same program. Think, play, repeat. Think, play, repeat. Think, play. It evolves into this extremely intricate pattern, and that's a metaphor for how physics works, and how the world works. We start with a few basic laws, and from those laws, we unfold all of chemistry, all the foundations of engineering, and empower ourselves to make and understand many things in the world. The other thing I wanted to convey with this is that science can also be artistic. Science can lead us to make new kinds of beautiful objects. So even if your inclinations are not necessarily scientific in the conventional sense, I think science needs also people with artistic creativity, and I think artistic art needs science too, to exploit the full potential of modern ideas. So there's plenty to do, and I've told you how to do it. I told you how I did it, and with that I'll conclude and take some questions. Thank you. Do you have a microphone or just talk loud?
As far as I know, in the past few decades, there were a lot of particle physics. They're highly experimental, but none of these results reach beyond the theory of quantum field theory.
Yes.
As far as I know, and meanwhile, there is a beautiful theory, string theory, but there is no feasible experimental thing to prove, verify the theory. And does it mean that at present it is more we should devote ourselves to the high technology rather than the theory?
Okay, so the question is that in recent years, really in recent decades, since the modern understanding of the four forces emerged largely in the 1970s and 80s, and by the year 2000 was very mature, progress has been slow. The Higgs particle has been discovered. Many details have been filled in. We understand the theory better. We can do more calculations. But the theory hasn't changed the fundamental theory hasn't changed very much. And meanwhile, there have been other more speculative ideas, string theory in particular, you mentioned, that have evolved, have come up, but have not been experimentally tested. Now, one thing I'd like to dispute your account is that there's not data to test the theory. There is data to test the theory. It's supposed to be a theory which describes the world, everything about the world. So you can test it by the fact, by all data. All data is relevant. Anything could prove it if you could calculate from the theory testable consequences. So it's not the world's fault that you can't check it. It's the theory's fault, or your understanding of the theory, that you have not been able to draw consequences that are testable. Now, so that makes a great challenge. Can you make the theory definite? Can you make the theory scientific? Because, I mean, a theory of physics that doesn't predict anything about the physical world is a pretty lame theory. So people are challenged. It's a big challenge to relate theoretical ideas to experiment. And to me, the magic of physics, the magic of science in general, and even the magic of mathematics is when you can take it from purely conceptual ideas and connect it to actual phenomena. Mathematics, okay, of course, it's in some sense a world of pure ideas, but even there, if you can make predictions about what will happen if you do some complicated calculation on a computer, that's a prediction. You're saying something about a real process. That's what I'll say. So that's the answer. The answer is you shouldn't blame nature. You shouldn't blame the experimentalists. If you have a theory that makes enormous claims, but you can't verify it, it's not because the experimentalists have failed. It's not because nature has failed. It's because you have failed. Okay, so if I understand the question, and there was a stage of translation where things may have gotten lost. The question is, this first of all, a statement that according to physics today, the universe is finite and bounded, and then the question is, what's outside? And the first part of the question is not correct. Physics does not conclude that the universe is finite and bounded. Perhaps what you're alluding to is the fact that because the speed of light is finite and the universe has only a certain age, we can only see out a certain distance, because larger distances haven't yet, the light from larger distances hasn't yet had time to reach us. Not light, but so any kind of it. From things that haven't had time since the beginning of the universe to reach us, we don't see yet in any sense. But as time goes on, we see more and more. In astronomy, we say that our horizons are growing. So the horizon used to be very small. It gets larger as time goes on. And there's nothing outside. If the universe were, if there was something outside the universe, we'd just say the universe is bigger and put that in. Again, I can only interpret your question, and maybe what you're asking is, okay, in some models of the universe, which are not presently the ones that seem the most promising, the large-scale structure of the universe, if you look at it as at fixed time, and look at its shape, is a gigantic ball. This is called a closed universe. And the ball may be getting bigger and bigger. That can account for the expansion of the universe, but it might very, very, if you look far enough, eventually past our horizon, you can see that this curve, like the Earth, that eventually closed up. But again, if that's the way it is, if the universe is closed in that sense, you have to think of just the surface of the ball being the whole universe. The ball is a four-dimensional ball with a three-dimensional surface, which is the actual physical universe. The stuff that's inside is not physical. It's just where you put this imaginary ball. Yeah.
Recently, the artificial intelligence has gained great popularity.
Yes.
Do you think the AI will outsmart human brains one day? And what's the advantage of AI compared with that of robots?
A robot. Okay. So the question is, do I think that AI, artificial intelligence, will outstrip human intelligence someday? That's one question. Okay. Let me answer that question. I do think so. I'm not sure how long it will take. I don't think it will be very soon, because we really don't understand what intelligence is. I mentioned this issue of neural networks, and that you can train neural networks to recognize cats. But it takes a long, long time. You have to show them many, many examples before they can recognize a cat. They're nowhere near as good at it as human children. The kind of computers that have learned, the kind of programs that have led to the success of computers in chess and in Go, so very intellectual games that we thought to require tremendous intelligence, and do in a certain way. They're not based on neural nets, or only very partially. So we understand how those work. They work by doing think as we understand neural nets better, as computers become more powerful, I don't think there's any clear barrier to superhuman performance on many tasks. Whether we want to make such things is a different question. Whether we want to concentrate or make general purpose intelligence that not only plays Go well, but also plays chess well, but also recognizes cats, and also can move around, and also can, I don't know, compete for mates. I'm not sure we want to do that. I'm worried that one big motivation for artificial intelligence in practice is to make sophisticated artificial soldiers and artificial weapons. But I'm not sure. So it's a complicated question. I don't know the simple answer. But if you believe that the basis of mind is physics, is matter, then I think you have to believe that if we understand things very well, since we know how to work with matter, we know the equations, that we'll be able to make things that mimic the human brain. And because we can make artificial things very, very small in great numbers, and because we can make them operate very fast, because they don't require such complicated metabolism as animals do. They don't require food. They don't require sleep. Yes, they will. I think it's hard to imagine that they won't exceed human intelligence in the long run. On the other hand, we have a few decades left, probably, where humans are on top as far as intelligence is concerned. And even in the long run, I think partnerships between artificial and natural intelligence will be very, very fruitful. We already have them. We carry around an iPhone, which has a lot of intelligence. But the hybrid iPhone plus human is much more intelligent than just the human, and much more intelligent than just the iPhone. So these things can be our friends. Okay. Yeah.
It's pretty privileged to meet you here. My question is more of a social one.
Yes.
So nowadays we often need to raise more money to in order to get some breakthroughs in physics. You know, we
Yes.
we need those expensive laboratories and facilities in order to get our theory toward some breakthroughs. But back in those days we would stick to the brain and pen on the paper to do some whiteboards, and we would get those data we coordinate in the experiment. But nowadays there are people out there saying that it's more important to get into a physics laboratory than to calm down and do the paperwork. So what's your opinion on this situation?
Well, it's complicated. Again, let me rephrase the question. The question is that as science becomes more sophisticated, the easy things get done. That's just true. And the questions that are still open are open because they're very difficult to investigate, like in particle physics. You need fancy accelerators. In dark matter searches, you need new kinds of telescope. We don't even know what they are, but certainly have to be new. And those things can be very sophisticated. They can be very sophisticated. They can require teamwork to construct. They can require expensive components. And that's true. However, that's always been true. Really. There's a kind of mythology that in the good old days, science was much simpler, that it was really easy. People would just sit down and think and scratch their chins and come up with the answers. But really, that's an oversimplification. education, for instance, we can look at history. By the way, one thing I didn't include in my advice that is very, very important and also fun, that's the good news, is to study history, especially the history of science, biographies of people. You learn that first of all, it stimulates the imagination. You have to put yourself in their position, but it also is inspiring. It teaches you lessons about how science is done. Also, by reading the masters, you can begin to understand their thought processes, and you learn from how they communicate, you learn a lot. Okay, back to the question. Kepler's great discoveries required very, very detailed, big science of Tycho Brahe's observations, and Newton's work depended on Kepler's very, very detailed calculations. I think it is true that the number of people involved used to be much smaller, and the pace used to be much slower. So it's difficult. It's more difficult for any one person to make a huge impact. But if you explore, if you look around, if you find what you think is promising, if you can identify what you think are weak spots, that's still the process. So I guess the bad news and the good news is that the world of science is much bigger. So there's more competition. It's hard for any one person to stand out, certainly in the beginning of their career. But the good news is that there are lots more opportunities too. So the challenge is you have to match your own talents to the opportunities. Okay, we have one more over here, and then you, and then we're done.
Yes. I was asked something about the dark matter. Do you think it really exists? Or it's just something wrong about our theory? Yes. I know that there's so-called nothing was found in some famous project of Planck,
Yes.
the project X.
Yes.
Okay, yes. How do you think about it?
Well, okay, so the question is about dark matter. Do I think there is such a thing? It was a more sophisticated version of that, and I'll address it. And then, I'll address it. So what do you mean by saying there is such a thing? Well, there's certainly a phenomenon, which is the phenomenon I mentioned, which is that in many, many circumstances, so I mentioned if you look at galaxies and the motion of the stars and clouds within galaxies, the gravity of the stuff that you can see is not enough. So you need more mass. That's not an isolated phenomenon. So it applies to galaxies. It applies to clusters of galaxies that move around each other. It applies to the whole universe, if you study cosmology. The amount of mass that's needed to account for how the early universe was expanding also needs dark matter. If you want to understand how galaxies form, you need dark matter. So there are many, many indications that there's something else. Now, I think the second part of your question is many people's first reaction to this situation is, well, clearly you got your equations wrong. that gravity doesn't work the way you think it does. And people have certainly explored that possibility quite a bit. But our theory of gravity, general relativity, has many, many successful consequences, first of all. And secondly, is very, very difficult to modify. It's based on equations that are very precise, very delicate, have enormous amounts of symmetry and special properties. And so it's very, very difficult to change the theory without ruining everything. On the other, but on the other hand, if you just add, so if you just add a particle, and it does what particles do, kind of move around in an ordinary way. It doesn't even have to interact with itself. It can be particles that only respond to gravity. Then it accounts, at least roughly, for the phenomenon. And that may sound like a strange, I mean, it would sound like a desperate hypothesis. Okay, you don't see anything, so you say, well, there's something we can't see that's out there. But that has happened several times. The discovery of the planet Neptune was based on the fact that the motion of Uranus, the planet Uranus, wasn't what was predicted by the theory of gravity. So people hadn't seen it, so there wasn't enough mass to account for how Uranus was moving. So people say, well, maybe there's another planet that's missing, that's responsible. So dark matter has to be responsible for this. And the calculations point to where it would have to be. And people look, and there it was. Similarly, the particles called neutrinos were introduced because when particles decay, they seem to violate the conservation of energy. Where's the energy going? There's something missing. But nothing was visible. So it was a desperate hypothesis that there was a new kind of particle. Very, very difficult to observe, and that's why you haven't observed it. When Wolfgang Pauli, who introduced this idea first, talked about it, he said he was very embarrassed by this. He said he's committed the greatest sin a physicist could ever commit. He's made a hypothesis that can never be checked. But of course, eventually, as experiments improved and people understood things better, they were able to detect neutrinos, and now they are the foundation of many, many techniques in physics that have given us a lot of insight about how the world works and generated quite a few Nobel Prizes in the process. So there is precedent for this, and not only that, but there are theoretical ideas that do suggest, that are very attractive for other reasons, that do suggest the possibility of new kinds of particles that would, if they exist, play the account for the dark matter. And they're very, very difficult to observe, but not impossible. So a very important frontier, and the one I think is correct, is called axions, which I named and invented. So of course I would think it's correct, but and it's very exciting now that people are mounting the kinds of experiments that have a chance of seeing this dark matter. So Panda X is one attempt to take another kind of promising idea about dark matter, called WIMPs, weakly interacting massive particles. This is a remarkable achievement that this laboratory, which is relatively new in China, has the world's best constraints. So it did have a chance of finding it, but so far the result is negative. But it's not over, because if you don't see it, look harder. We're going to build a bigger one, and look harder, and maybe there'll be big moves down the line. Okay, so I think, thank you very much. I think.